Let's begin the second part of this talk. And now we move on to the non-compact solutions to mean curvature flow. And let's consider the following example. So suppose we have a complete convex graph over a ball. Yeah, it's drawn here. And well, let's think about it. Its behavior under the mean curvature flow, yeah, and also asymptotic to the cylinder, enclosing this hypersurface. Well, Sayers and Schnurrer have showed that under the mean curvature flow, this graphical solution will remain smooth and also asymptotic to the shrinking cylinder, and it's going to move basically at a later time. This is what we see, yeah, at a later time. And also, the surface will eventually disappear at spatial infinity at the same time as the cylinder collapses. Okay, so we can think of this as a sort of a cylinder, singularity occurring at infinity. Okay, so near this vanishing time, capital T, what happens? Well, if we just focus on the leftmost point, yeah, the tip here, well, we see it has traveled infinite distance, yeah, in a finite amount of time. So we should expect that the hypersurface is moving at a very high speed, which is suggesting that there must be some kind of a high or fast curvature blowup. And this raises the question, the following question. Yeah. So what can we say about the precise asymptotics for such a solution near a capital T? Okay, so to answer this question, this is some joint work with Eisenberg and also Zhou Zhang. We have the following result. For each real number gamma that's greater or equal to a half, and it's actually worth mentioning, this theorem comes into two parts. The part when gamma is strictly larger than a half is done with Jim, and the case when gamma is equal to a half is joined with Jim and Zhou Zhang. Okay, and what's the result? Well, the result says that for each such gamma, there exists an open set of complete strictly convex graphical hypersurface defined over a ball, a shrinking ball, and also asymptotic to cylinder at infinity, so that we actually see type 2A curvature blow up in such a solution, and the highest curvature happens at the tip. Okay, so let me again draw the picture here. So the highest curvature occurs here, and it's type 2A rate. And the solution now comes sort of we can also define or describe the solution, what's near the tip and what's near spatial infinity. So in particular, the solution near the tip will be modeled on the bow soliton, and the solution at infinity, well, we know it will remain asymptotic to a cylinder, but in fact, it's asymptotic to a cylinder at a precise rate depending on gamma. Yeah, I'm not writing it here, but the precise rate depends on gamma. Okay, so this is our result in the non-compact case. So as I said, right, so we can think of this as a sort of a degenerate neck pinch that occurs at spatial infinity. Okay, so now let's, before I move on, let me also add a remark. So if we recall the result by Angan and Velasquez, right, so in their result, the curvature blow-up rate is T minus to the power minus 1 minus 1 over m. And if we let m go to infinity, then we get the type 2A blow-up rate of 1 over, yeah, capital T minus T. And this case, you can think of it as, sorry, let me use a different color here. you should think of this case as the sort of the limiting case corresponding to gamma equal to a half here, because when gamma equal to a half, this is also -1. Yeah. So somehow gamma equal to a half can be viewed as a sort of limiting case of either sending gamma down to 1/2 or m equal to infinity. But it's just a special case in terms of the curvature block rate here. Okay, that's a remark. And the second remark is that in Angolan and Velasquez, the curvature block rate is a discrete set, yeah, given by the integer m, whereas here we have a continuum in terms of the curvature block rate, yeah, because gamma is any real number greater or equal to a half. Okay, so this is the statement for our results. And now let's go over the idea of the proof. So the idea is pretty straightforward. Well, first of all, we are assuming, we're making the assumption of rotational symmetry. Yeah? So this is a big assumption in a sense. It reduces the mean curvature flow system to a single quasi-linear parabolic PDE of a scalar function. And of course, this would help us to apply a rather detailed analysis, in particular the matched asymptotic analysis, where we would construct approximate solutions in suitably rescaled coordinates. And with this, then we can come up with sub-solutions and super solutions to our PDE. And so again, in different regions, okay? So, and in the end, along with the comparison principle, we will see that the barrier, we will use the sub and super solutions to construct the barriers. And then, yeah, let me draw it. So basically, this is what we eventually will get. So we have super solutions in two regions, and then we take the inf of the super solution. This will still give us a super solution. And we can take the sup of the sub-solutions. This will give us, again, a sub-solution. And then by suitably ordering them, we will make sure the super solution stays above the sub-solution, and therefore they form the barriers for our PDE in the rescaled coordinates. And then we are almost in business, because then if we apply if we construct a solution, initial condition between these barriers, and we run the main curvature flow starting from such an initial condition, then along with the comparison principle, we will make sure that our solution is always, it always stays between the barriers. Okay, and now because of the way we have constructed our barriers, and we have in fact the precise asymptotic information of the barriers, then we will be able to then deduce the precise asymptotics for our solution based on this barrier. So this is the main idea of the proof. Okay, and now let me go into some of the details. Okay, so first of all, for rotationally symmetric mean curvature flow, and if we consider a graph, so let's say this is a U of X, the profile, right? Now, also as a function of time. Now, the mean curvature flow for a graph is also a rotationally symmetric graph is given by equation 1. So it's actually quite, it doesn't look too complicated. And let's also make some assumptions here, right? So we're going to assume U is increasing concave and it's approaching some horizontal asymptotes, yeah, as we tend to spatial infinity, as X tends to infinity. Okay, and this is the equation in the unscaled X and T coordinates. And now let's introduce some rescaling And in particular, what do? Well, if, okay, from now on in the talk, we will assume gamma is strictly larger than a half. And we will basically introduce the following rescaling. So we will rescale the time so that it's defined from some finite number to infinity for the tau parameter. And we will rescale the height of the graph by the type 2 rate. Sorry, by the type 1 rate. So we write it as phi. And then we also rescale our x coordinates. Well, because right in the unscaled coordinates, our hypersurface is moving towards infinity, and this just helps us to bring it back. Yeah, so we sort of want to renormalize in some sense, renormalize the yeah. And this is the rescaling we're going to apply when gamma is strictly larger than half. And if gamma is equal to a half, then we apply a different scaling. Yeah, because and the subsequent analysis will differ, but the strategy of the proof is still the same. So in this talk, let's just focus on the case when gamma is strictly larger than half. Okay, so now in the y and tau coordinates, then PD1 becomes the equation 2. Okay, so it looks a bit more complicated, but then we can, okay, and also because of the let me move on. So because of the geometry here, right? Because our phi, because so let's see, y and phi. So because of the geometry, we can also turn our head sideways, and we can invert the coordinates and view it as so write it as a graph over the domain in phi coordinates. So after inversion, then the previous PDE just becomes this PDE. Okay, now we apply our sort of formal analysis and say, okay, if we, because tau eventually tends to infinity, so if for the moment we ignore this, and also let's sort of seek a stationary solution, we ignore this term. So in the end, we ignore these two terms. Then this PDE is approximated by the following ODE, and we can actually solve it explicitly to get the following profile. Okay. However, such approximation is only valid when phi or phi times e to the power gamma tau is large. Okay. And where this quantity is large, we'll call it the exterior region. Now, where the quantity is not so large, we don't call that interior region. And to understand what the solution looks like in the interior region, we'll introduce a further rescaling. So here we define the z to be phi times e to the gamma tau. And with this in mind, it turns out that we can find a formal solution to this equation for y z tau, and this is an ansatz. In particular, the profile or the function p tilde here is a solution. It's basically the profile for the both soliton, namely it's a solution to this ODE initial value problem. Okay. Now, this tells, and what's more, we can write down the precise asymptotics for the both soliton profile, which is the function p tilde, and it's given here. In particular, the asymptotics near z equal to 0 implies that in the original unscaled coordinates, that is x and t coordinates, my function, so this is u and x. So the profile here looks like, or is given by the equation here. And in particular, what's written in blue is the most important part, namely x, it's basically a quadratic for u near u equal to 0. Great. So this tells us the following sort of features of the formal solution. Well, the highest curvature, okay, can be shown to occur at the tip, which is where u equal to 0. And also, that point happens to be umbilical. So we can actually compute the curvature there. And in particular, the mean curvature at that point, at the tip, is this quantity. And we see that if gamma is equal to a half, is larger than a half, then it is in fact type 2. Of course, I mean, as long as gamma is strictly positive, then it's type 2. But for our case, we do want this. It's because when we look at the displacement of the tip, right, we just integrate the mean curvature, then we realize it's infinity if gamma is strictly larger than half, or gamma equal to a half. Yeah, because when gamma equal to half, integrating 1 over capital T minus C gives us the log, and it's also tends to infinity as we approach the vanishing time capital T. So the parameter gamma greater or equal to 1/2 is in agreement with the picture we saw in the beginning, namely the hypersurface is moving towards spatial infinity. Okay, what else? Well, so in the y coordinate, right? After we renormalize, we see that the tip basically stays a finite distance away from y equal to 0. So we can then sort of carry out some analysis in this coordinate. And also, because our solution now comes from two regions, one is in the interior region and another is in the exterior region. So we have to, sort of figure out what's happening in between. So this is basically the sort of matched asymptotics. And to match the solution from the interior region to the solution from the exterior region, it turns out that we have to arrange the two parameters. Yeah, this is from the interior region and this is from the exterior region. We have to make sure they satisfy this relation. Okay, so this is, the matched asymptotics. All right, what's more? Now, so this is, so far, it's again a sort of formal discussion, and let's continue. It turns out to carry out our analysis in our proof, it's better to work with a different set of coordinates. So we work with, instead of function y, we define lambda to be minus 1 over y. So this basically gives us a bounded function defined on a bounded domain. Because previously y, right, is defined, y takes value from finite number to infinity. Okay, and what do we have now? Well, if so what's the evolution for lambda then? Well, it's basically given by equation 3, right? So again, it looks rather complicated, and but let's not worry about it, because we've already sort of explained how to get the formal solution for y, and we can apply a similar argument to obtain the formal solution for lambda in the two regions, the interior region and exterior region. In particular, in the interior region, the formal solution is this. So A here is some constant to be chosen, and F is basically a rescaled low soliton. Whereas in the exterior region, we have a really precise formula for the profile. Okay, so this is our formal solution to the PDE. Okay, so what's the point of constructing these formal solutions is that we're going to use these formal solutions and modify them to obtain sub and super solutions to the PDE. So let me first sort of record the definition, right? So we say the function u is a subsolution to the heat equation, yeah, if dt minus Laplace u is less equal to 0. Or we say it's a subsolution if this is less equal to 0, or super solution if this is greater or equal to 0. So we can apply the same definition to our mean curvature flow equation in the rescaled coordinates. And in the exterior region, we have the function lambda, depending on phi and tau. It satisfies the following PDE, right? It's this piece, but whatever that is, we define an operator F, based on that. And the PDE is this. So the operator F applied to lambda equal to 0. And in the interior region, lambda satisfies an even more complicated equation, but again, we can just define a parabolic differential operator. This time we call that T, acting on lambda. So our equation is basically in the exterior region, F acting on lambda is 0, whereas in the interior region is tau acting on lambda is 0. And in each region, we'll construct the corresponding super solution and sub-solution. Right? So for the super solution, we want the operator acting on it to be greater or equal to 0. And whereas for the sub-solution, we want this to be less equal to 0. Okay? And the point or the message is this can be done. And how do we do it precisely? So let me actually give you the statement. So in the interior region, right? Remember, in the interior region, the solution, the formal solution we constructed before is given by, right? So maybe let me call that. This is just our formal solution. But it turns out that we can modify it on the lower order terms. And that's given by what's written in blue. And as long as, and with this appropriate modification, then we can show that on the region, on the space-time region where Z is between minus R1 and R1 for some R1 fixed, and for sufficiently large tau, then this defines the sub-solution and the super solution in the interior region for us. Okay, and of course the proof is to verify such a definition. Yeah, when we apply the T operator to lambda plus, we get a greater equal to 0. And when we apply the T operator to lambda minus, we get it's less equal to 0. Okay, so so the message is we can construct sub-solution and super solution in the interior region. And similarly, we can construct sub and super solutions in the exterior region, right? So remember, this is the formal solution in the exterior region. And again, what do? We are going to sort of modify it, and then we can come up with super and sub-solution in the exterior region where the region is defined for this space-time. Okay, so phi is between R2 times e to the minus gamma tau and square root of 2n minus 2. Because when phi is square root of 2n minus 2, we hit the asymptotic, we hit the cylinder, yeah? That's enclosing the hypersurface. And as we said before, right, let me just redraw this picture. Now we have in the interior region, super solution and sub solution. And we also have in the exterior region, super solution and sub solution. We just have to, and also we can choose our R1 and R2 so that these two regions overlap. And then after some further work, actually after, not say some, not to diminish the further work, but after further work, we can arrange these sub and super solutions in the appropriate order so that we can come up with global sub and super solution to our PDE for lambda depending on phi and tau. Okay. And once we have these global sub and super solutions, they also act as barriers. And because in our construction we have precise information of these barriers, then we will in fact then obtain the precise asymptotics for our solutions. That's always sitting between, that always sits between the two barriers. Okay. Yeah. So this sort of concludes the results on non-compact solutions to mean curvature flow that that has type 2A curvature blowup. Now, what can we say about the stability, right? So this brings us to some more recent work, which is joined with David Garfinkel, Jim Eisenberg, and Ben Knopf. So where we have carried out a numerical study on the stability of non-compact type 2A solutions that we just we constructed earlier. So first of all, let's say we consider so-called a near class. So the near class is basically where we are perturbing the solution near the tip. And here, our perturbed solution is also rotationally symmetric. And we see that under the sort of a numerical simulation, we see that the solution, right, eventually forms something, becomes a profile, and the solution seems to still seems to be developing a type 2A singularity as we constructed earlier. Okay, and here this is just unscaled curvature at the tip, and here's the curvature rescaled according to capital T minus T to the power minus gamma plus a half. And this is a simulation for dimension n equal to 2 and gamma equal to 3/4. So for the near, so basically we observe there's a near class of initial data, or there's a near class of initial data that's close to our unperturbed solution, right? So maybe let me draw the unperturbed solution. This is our unperturbed solution we just discussed, and so this develops a sort of type 2A singularity near the tip. And there's a near class which still seems to be developing the same kind of singular behavior. On the other hand, there's a far class of initial data, so that if we perturb it, so this time not so close to the tip, but more closer to the cylindrical end, then we realize, or then we see, according to this numerical simulation, that it's forming a non-degenerate neck pinch. Okay, and again, this picture is the simulation for n equal to 2 and gamma equal to 3/4. So, okay, so this is kind of interesting in the sense that, okay, so we have two kinds of behaviors, right? So, so again, let's say this is our unperturbed solution. Now, if we apply some perturbation here, then we see it still has the same kind of a singular behavior. But on the other hand, if we apply a perturbation here, then we see something like this, right? It's probably more extreme. And this is a sort of type 1 non-degenerate neck pinch. So somehow, if we consider whether or not certain singular behavior itself is stable or not, then we see that at least locally, yeah, for the red curve here, locally this behavior seems to be stable, but not when it's far away. I mean, locally near the tip here. Okay, and of course, we can ask ourselves, what happens when we move this perturbation in between, right? What happens? So I guess it's very natural to come up with the following conjecture, namely that we might have some intermediate behavior, yeah, that's neither the type 2A singular behavior that we've constructed before, nor the type 1 behavior we have seen. And here is precisely the conjecture. Yeah. So this is redundant. So basically, this is we conjecture that there exists the following solution, right? So it's basically a sort of non-compact version of the type 2A singularity, or sort of non-compact analog of what's obtained by Anglin and Velasquez before. And here's a statement: it's conjecture a solution in the critical class. So we conjecture the existence of a critical class, and a solution in this critical class develops a local type 2A singular degenerate neck pinch, whose precise asymptotics are the same as those given by Anglin and Velasquez. Okay, so this is the evidence. And of course, as we said, the numerical analysis we have carried out so far, they only we've assumed the perturbed solution still remains rotation symmetric. And of course, we can ask, right, what if we relax this assumption? What if we just consider graphical, more generally, just a graphical perturbation of our solution, and then whether or not we still see this kind of at least a local stable sort of phenomenon when we perturb the solution near the tip. Okay. Yeah. So that's all I want to say, and thank you very much for your attention.